Hello, hello everyone to the seventh tutorial of the course Introduction to Classical Mechanics. So today we will do some problems on the rigid body dynamics. Mainly today we will focus on the moment of inertia tensor, and we will try to calculate the moment of inertia for various types of body. So let us start. Okay. So as you know that our moment of inertia tensor is denoted by ijk, where it is a tensor. So moment of inertia tensor. Now how this looks like? So this looks like m I r square I delta jk minus xji, sorry, xki, this one, where I have explicitly written the I with every term like mass, distance, xj, xk, to give you the idea that it is summed over all I, where I is the number of particles in a rigid body. Okay, so a rigid body is a combination of many particles, so we will consider every particle. That's why we have summed over all the particles, and the component jkth component are shown by this j and k explicitly, where like here in the second term in the parenthesis, that xj and xk. So xj xk are xj I xk I correspond to the xj and xk coordinate of the particle I particle, I mean ith particle. So that's how it is written. Now let us consider some physical situation. So at first we will take a simple example of diatomic molecule. Okay, so in this diatomic molecule we will consider two atom like this, and let us say this is the axis. So this is x2 axis, it is x3 axis, it is x1 axis. You can write it as xyz also, no problem. And this is the origin. So our distance r1 of this first atom from the center is r1, which has a mass m1, and it has a distance of r2 from the center and has a mass m2. And we are neglecting the radius of the atoms, I mean we are treating as a point particle, so that that's why we are neglecting the radius of that particular atom. Okay, so as for this particular system, our O is the center of mass. So we can write that 0 is m1 r1 plus m2 r2. Okay, 0 is the center of position of the center of mass. So if we write it in vector form, so r1 you can see r1 is directed as to negative x2 axis, where r2 is the positive x2 axis. So that's why r1 can be written as r1 minus x2 cap, where here this r1 is only the magnitude, plus m2 r2 x2. So we have taken that x2 cap is the unit vector along the x2 direction. Okay, so that is 0, and if you calculate you will get, this is easy, m1 r1 equals to m2 r2. Okay, so using identity of mathematics, it can also be written as r1 by 1 by m1 plus equals to r2 by 1 by m2 plus to r1 plus r2 1 by m1 plus m2. This we can write using the identity of mathematics. I have forgotten the name of the particular identity. So and you can see the denominator is 1 by m1 plus 1 by m2, which is actually 1 by mu, where mu is the reduced mass. So you can write it as mu A. Okay, where A is actually R1 plus R2, the distance between the two atom. Okay, so this is this is what we can write. Now we will calculate the moment of inertia. So as you know, our moment I have written our moment this expression ijk. So first we will calculate the I11, or you can say Ixx. So that is summation over m. So it will be r square delta jk, that means delta 11, that is that is 1, minus x j, that means x1, and x2. Okay, yes, this one. Now sorry, x1 because we are considering the ii component, that is 1 component. So as you see, our molecule is oriented along the x2 direction only. So there is no x1 coordinate in this particular system. That's why we can write it as m I r square will be x2 square only. Okay, because there is no x1 and x3. X1 and x3, all x1 and x3 are 0 for this particular system, because it is oriented along the x2 direction. Only non-zero coordinate are x2. Okay, so this we can write as m1 r1 square plus m2 r2 square. Okay, so this is your 1 component of inertia tensor I11. Similarly, if you calculate now I22, that is Iyy, then you will get your r square is always x2 square. You don't have another I mean, ideally it should be x1 square plus x2 square plus x3 square, but you don't have x3 and x1. That's why it is only x2 square and minus x2 x2. That means minus x2 square. So your x2 square is also cancelled and your I22 equals to 0. Okay. Similarly, your I33, here as usual it is only x2 square and it is x3, but you know that all your x3 coordinates are 0, so that is 0. That will only give you mi xi, I mean x, I should write it x2i square. Okay, so this is m1 r1 square, m2 r2 square, because always remember your r1 and r2 is along your x2 vector. That's why we are writing it. So from here you can see I11 equals to I33 is m1 r1 square plus m2 r2 square, but your I22 is equals to 0. Okay, for this particular system. So a diatomic molecule where we have considered our that is along the x2 direction, and it is only a linear type of molecule, so there is no x1 and x3 coordinate in this particular system. That will give you non-zero moment of inertia along the x1 x3 coordinate, that means Ixx or I11 and Ix and I33. So this is along x1 and this is along x3, but your x2 along the x2 coordinate, which is your along which your system is here. So along that coordinate you are getting a 0 moment of inertia. Okay. Okay. So this is a very simple example. Now we will go to another example, which is a thin rod. Okay, thin rod. Okay, suppose we have same x, y, z coordinate, and your rod is along y direction again. So this is your rod, thin rod. We will consider, I mean it is like 1D rod. We will not consider the breadth, just the length. Okay, so that's why it is a thin rod. So this thin rod, and it is not a rod, it is rod along y-axis. That means all your xi equals to 0 and all your zi equals to 0 for this particular system, same as before. Okay, so you can write your xx as m I delta xx is 1, that means r square for ith particle minus I can write it x for ith particle and similarly x coordinate for ith particle. Okay, so this will give me mi r square. Here also r square is the summation of x1 I mean x square plus y square plus z square, but there is no x and z in this particular problem. That's why same as before, it will give you only y square, and this is also 0 because x I equals to z I equals to 0. Where you find any x coordinate or z coordinate, you can put 0 there. So that's why it will be like this, or you can write it m y square. Okay, m I y I square. Okay, because y square corresponding to that ith particle, that's why it is denoted at y square I. Okay, so this will be same as izz, similar to the previous case, and your yy will be 0 because in this part you will get y square minus y square, that will give you 0. Okay, so now we will calculate ixx. Now if we consider the rod as a continuous body as it is, so then we can substitute our summation sign with the integration sign, so that mi square, it can be written as y square dm. Okay, we are summing over the mass of the rod, and what will be the limit? So suppose the length of the rod is L, and our center of center of the coordinate system is 0. So here it is L by 2 and here it is L by 2. Okay, so y is running from minus L by 2 to plus L by 2. So we will integrate over that particular range, and yes, and another thing, okay, so this will be the integration. Now dm, so dm is the mass of a particular portion, I mean small portion of that rod. This dm can be written as lambda dl. Okay, and for our case L is along the y coordinate, so we can write as lambda dy. Okay, so what is lambda? Here lambda is the mass density. Okay, so we have considered a constant mass density of lambda, that of the rod. That's why we can write the mass as density times the volume. So there is no as we are considering a 1D rod, so the volume will be replaced by the length, that is so that's why the mass is lambda times dm. I mean small mass is lambda times dl. So we will write it as y square lambda dy minus L by 2 to L by 2, sorry, L by 2. Now if you do this integration, you will get L cube by 12, lambda L cube by 12. Okay, so ixx is lambda L cube by 12. Now this is correct, no problem in that, it is fine, the result is fine, but we always want to express our moment of inertia tensor in terms of mass of the body. So which body we are considering? So as we have a rod of length L, density lambda, then the mass, the total mass of the rod is actually lambda times L, right? Lambda times L. So this we can write as m, where m is the total mass of the rod. So if we substitute here, then we are taking lambda L outside and L square by 12. So that will give you m L square by 12. Okay, so your Ixx is m L square by 12, and if you calculate your Izz, it is also same m L square by 12, and your Iyy will be 0 for this case. Okay, so what does that mean? Suppose this is your rod. So this is your rod, and this is the z axis, this is the x axis, and this is, which is coming towards me, is the y axis, suppose. Now if your rod rotates like this along centering the z axis, then you will get a moment of inertia of the rod which is equal to the ml square by 12. Similarly, if the rod moves like this, centering around that vector which is coming towards me, suppose say that is x, so it is rotating like this. So if the rod is rotating like that x axis, then we will get an inertia which is also ml square by 12. So this rotation and this rotation both have same moment of inertia for a symmetrical body. Now another axis is the axis which is passing through the rod, which is not perpendicular, which is along the rod. So if the rod is rotating along that particular axis, it will rotate like this, only this, you can see. So for that particular case, we are getting a moment of inertia which is actually 0. So this is the three particular thing for which we are for this particular system which we are considering. So the moment of inertia along the perpendicular axis, those axes which are perpendicular to that body, the rotation about those axes will give you a non-zero moment of inertia, while rotation of around that axis which is along your rod, that this type of system rod, or this type of 1D system, so which axis is going through that particular rod, that rotation around that axis, that will give you a moment of inertia of 0. That is what I want to say from these two example, which was the diatomic molecule as well as this thin rod. Okay, so as the rod was along y axis, the moment of inertia along y is 0, but x and z are perpendicular to the rod. That's why we got Ixx and Izz non-zero values. Okay, now for this two case, I have not, for this two example, I have not calculated that Ixy or Iyz or Izx, because whenever you will calculate, suppose Ixy, okay, so the first term will be 0, because the delta ij, there is a delta ij, and if I and j are not same, for I not equal to j, the first term will be 0, so no need to write this term. Only the second term, which is xi and yi. Okay, so as you know, for this particular system, all the xi are 0, so that is 0, it will give you Ixy as 0. Similarly, if you calculate Iyz, Izx, all this will give you the 0. So the cross component of moment of inertia tensor will be 0. Only the Ixx and Izz non-zero component will be there. Okay, so this rotation, what I have done till now, was around this point, which is the center of frame, that is O. Now what will happen if we consider the rotation of the rod, same rod, but now the rod is here and the center is this one. Okay, so from the center O has been shifted from the center of the rod to the edge of the rod. Okay, the origin has shifted. Now for this case, similarly, Ixx, so for the previous case, what was our Ixx? That was minus L by 2 to plus L by 2 y square dm or y square lambda dy. So the same thing will be here also, but this time our integration limit will be 0 to L, because the rod starts from this point O and it ends at this point, so the distance is L. Okay, so instead of plus L by 2 and minus L by 2, which was in the previous case, it will be 0 to L. And if you do the integration, then you will get as ml square by 3. Okay, yes. So yeah, so you can see that let me okay, yes. So by choosing the coordinate system properly, you can, I mean, you can get different value of the moment of inertia tensor. It depends on which axis, which is the your center of center of mass of the, I mean, which is the origin of your frame. If your origin is at the center of mass, which was in the previous case, you get ml square by 12. But where your center is not at the origin of, I mean, origin is not at the center of mass, but it has shifted to the edge of a rod, then you will get a different value, which is ml square by 3. Okay, so this is the difference. So let us call it ixx dashed, and in the previous case it was ml square by 12 when our origin was at the center of mass of the system, that means at the midpoint of the rod. Okay, and this is this will, I mean, this shifting of the origin of the system, this is called the perpendicular parallel axis theorem. I mean, you can use that parallel axis theorem also, but I think you have not taught that theorem till now. So when it will come, we will talk about it, the parallel axis theorem. Okay. Okay. Now we have done the diatomic molecule, the rod. Now we will do a rectangular lamina. So all these results are very important. If you can, I will ask you to remember, if you if it is possible to you, that ml square by 12 is for rod. So try to remember this. Now a rectangular lamina. Okay, so rectangular lamina means a rectangular sheet. Okay, y, x, z, and suppose L is the length and B is the breadth and this is the O. Okay, yes. So this is a 2D sheet which have xi not equals to 0, yi not equals to 0, because it is in the xy plane, but your all zi are 0 for this particular system. Okay, so if you calculate ixx, similarly it will give you mi, the r square, the first r square, it will be yes, x square plus y square plus z square minus x square. Okay, so x square will be cancelled out, and as all yi are 0, this will also be cancelled out. Sorry, zi are 0, not yi, zi are 0, this will also be 0. So it is mi yi square. Similarly, m y square dy. Okay, no, here no, I should not write it like this. Okay, so here I will write as dm. Okay, y square dm. Now for this particular lamina, what is our dm? So here, if the density, I mean density per area is sigma, and for a very small area this is, so for this particular element which I have shown in the figure, the area is dx dy. Okay, so the mass for the of that particular portion dm is sigma dx dy. Okay, so here the mass of this particular element is sigma dx dy, or dx dy is the extension of that particular portion. Now if we write sigma dx dy in the integration. Now the point is what will be our limit. So sigma is constant, y square dy, and always remember, if you give, suppose you have given some sigma as a function of x or function of y, that you can also do while you are doing the integration. Just sigma will not come out of the integration, and it will and you have to take care of that particular term properly. Okay, so for our case we are considering the sigma is constant. So and here our limit will be minus L by 2 to L by 2. Here this is the minus L by 2 and this is the plus L by 2. Similarly the b will be minus b by 2 to b by 2. So our center of the system is at the center of mass, which is at O. It is at the midpoint of the sheet. Okay, so if you do this thing, you will get similar result like before, ml square by 12. Okay, so for your rod as well as your rectangular lamina, you are getting same moment of inertia, that is ml square by 12. Okay, now yes, it is along x axis. Now what will happen for y. So I y will give you mi x square plus y square plus z square minus y square. Okay, y square cancel out, just z is always 0, so that is mi xi square. Okay, and if you do the same thing like I did before for ixx, so iyy you will get a same value, but the length will be replaced by the breadth, mb square by 12. Okay, so ixx and iyy we have done. Now the interesting thing is izz for this particular case. So what will be izz? Izz is x square y square j square minus j square. Okay, ideally it will be the situation, but for our case all z are 0, so it will be mi xi square plus yi square. Okay, which you can write as x square plus y square dm we will write as sigma dx dy. Okay, so this is your izz. Now yes, now if you write it in open form, sigma is out of the integration, so x square dx and dy will be there. Similarly the second term dx and y square dy will be there, and your limits are same as before, as L by 2 minus b by 2 minus L by 2 L by 2. So if you do this integration, it is very trivial. You will get m by 12 L square plus b square. So some interesting thing you can see from this three result. So this is your izz, ixx we calculated m by 12 L square, iyy m by 12 b square, right? So you can say that my izz is actually ixx plus iyy. Okay, okay, so this is also called as a perpendicular axis theorem. So it is valid only for a laminar body. Like for our case it was the sheet which was a laminar body, and what this was x, so this was x, this was y, and this was z. So you can see, if the the moment of inertia of that particular sheet, if it is rotating around the x axis and plus the y axis, so this two term is actually the rotation if it is rotating along z axis. So your perpendicular axis is z, that means the moment of inertia along the perpendicular axis is the sum of the other two axes along which the sheet, along which in along I mean in which plane the seat is actually is. I mean the seat is actually is x and xy plane. So that's why ixx plus iy is equals to the moment of inertia of the body if it rotates around the perpendicular axis, which is izz. So this is called as perpendicular axis theorem, and it is valid only for laminar type body. Perpendicular axis theorem. Okay, so whenever you are dealing with some this type of problem, suppose you have calculated ixx iyy, then you don't have to calculate izz, just write izz is ixx plus iyy for this particular type of body. Okay, okay, and for this case, so if we calculate ixy mi, and here it will be xi yi. Okay, the delta term is 0, that means xy sigma dx dy. So you can see this is non-zero because x and y coordinate are non-zero for this particular system. Only the z coordinate is 0, any z coordinate is 0. So if you calculate this ixy from similar way, that minus b by 2 to b by 2, minus l by 2 to l by 2. So by calculating this, I mean from here you cannot say it is 0, so I should not write it non-zero. I mean from here you cannot say it is 0 or it is non-zero. Okay, but after calculating, it may happen that you are getting 0 because of the symmetry of the body. That 0 is coming purely from the symmetry of the body, but generally from the expression you cannot say that it is 0, as we can say it for the previous case. I mean here ixy, you can say it here from 0 because there was no x coordinate, only y coordinate was there. So if you multiply your y coordinate with x, z, anything xy or zy, that will be 0. Similarly, there was no z coordinate, that why x, z, y, z all will be 0. So that you can say from the system itself that my x and z is 0. That's why all the cross product which have a x and z component, that is 0. But here you cannot say from the system itself, you have to calculate, and from the symmetry of the body, if you calculate, you will get it 0 also. Okay, so that is coming from the symmetry of the body. But it may happen that if you change your origin of the system O from center to any other position, and you calculate your I dashed xy with that particular position, that may be non-zero. Okay, so that may happen, which I mean I xy is 0, but I dashed xy is not 0. Okay, yeah. So for this particular problem, if you take your center O at a corner of the lamina, then if you calculate, you will get your I dashed xy minus xy sigma dx dy. Okay, and here x dx y dy. So here your limit will be 0 to l and 0 to b instead of minus l by 2 to plus l by 2, and if you calculate, you will get minus 1 by 4 mlp, which is clearly non-zero. That is the point. So for this case, your cross product may remain, may not also remain. That depends on which coordinate system you are choosing. Okay, this is a very important thing. Yes, but in the previous case, whatever coordinate, I mean center of system you choose, that O point, you will get the cross product always 0. Okay, that is the important point and the difference between these two system. So for this particular case, if you for this particular rod, if you shift your O point at the edge of the rod, then also you will get your cross product ixy as 0. But in this case, you are not getting the 0, you are getting a non-zero value. Okay, so you have to calculate, you cannot write it. But yes, but for this system, as all your zi is 0, so all the cross term which have a which have a contribution from the z coordinate, like ixz, iyz, those will be 0, whether you choose your center of the system in the midpoint of the seat or the corner of the seat. That doesn't matter, because the z is 0, that means your product will be 0. Okay, so ixx depends on ixy depends on O, and depending on that O, you will get 0 or non-zero value, but ixz and iyz is 0 always, whether you choose your O at the center or at the corner. So this is the important point. Okay. Okay. Just a second. Sorry. Yeah. Now, okay. Now we will do. It is important. Yeah. So just a second. Yeah. Now we will do for a triangular lamina. It was a rectangular lamina. So triangular lamina is relatively complex. To calculate it relatively complex. So let us pardon my drawing. So this is the rectangular lamina. Say it is the y-axis and it is the x-axis. Okay. Okay, and A B, it should be anti-clockwise, ABC. So let us consider it as xm. It is needed for the integration, that's why I am drawing it, you will see. Okay, so this one. Now suppose the z-axis is perpendicular to the lamina. Okay, that means z-axis is coming out of the plane, out of the page of the paper. Okay, and your this is O, where this O is the origin, this point is O, which is the origin, and OA is H. Okay, and sigma is the density as previous case. So all these are given. Now from this particular figure I can write xm by A. Okay, where A is this distance and B is this distance. OB is B, small b, OC is small a. Okay, so xm by A is actually h minus y by h. Okay, this we can write from the symmetry of two triangle, and it will give you xm as a 1 minus y by h. Okay, this we need for our calculation. Now as I have told that z axis is coming out of the plane of the paper, that means zi is 0 for this particular system. So ixx you will get y square plus z square dx dy sigma, and as z is 0, remove this, this will give you y square dy sigma and dx. Okay. Now what will be our limit? So for y is running, this is y is running from 0 to capital H, because our OA is capital H. Okay, the height of the triangle is capital H, and our x will run from 0 to xm. Okay, so xm is the maximum value of the x which we are considering. Now in this particular calculation we are considering our I mean our calculation only for the first part. So we have divided the triangle into two part by this OY line. So suppose it is the 2, it is 1. Okay, now we are now doing our calculation for the y part only. So if you calculate, you will get uh, I mean yes, so sigma y cube by 3 0 to h, and it will be xm, right? Oh, what I am doing, right? So yes, so this is the independent integration 0 to xm, which will return you only the xm. Now if you put your xm in terms of y, that will give you 1 minus y by h y square dy, 0 to h, right? So this is your integration, because your x was a dependent function of y. That's why you have to do the x integration separately, and then you have to carry out the y integration. So if you do this integration, yes, this will give you 1 minus y by h y square dy, where h is constant, and put these values. So you will get a result 1/6 m1 h square. Okay, so where m1 is half a h sigma. Okay, so this you will get from this integration for part 1. Okay, yes. Now you see that all this calculation ixx was for part 1. So we are getting that half m1 h square, where m1 is the mass of the part 1, which was half ah sigma. Okay, because the mass, I mean the area of a triangle, which is, say, this triangle, this part 1 triangle, it has a area of half into a into h, where a is the base and h is the distance. So a is the base of the part 1. So that's why half ah times sigma is the density. So density per area, so density in the into area, that will give you mass of that particular portion. Similarly, if you calculate ixx for the second portion, which is that left side of the oy axis, then you will get similarly 1/6 m2 h square. Okay, where m2 is the mass of the second part, that is half bh sigma. Okay, where b is the length of the base of this particular portion, and h is the height. Okay, so yeah, this will just a second, I have yes, I have yes, m2 h square. So it is ixx for the second part. Now the total is ixx, so let me write this 1 and 2 to denote it the first part and second part. 2. So this will give you m1 plus m2 h square, which is 1/6 capital M h square. So capital M is nothing but m1 plus m2, the total mass of this triangular lamina. Okay. So this is your ixx, 6 capital M h square, where m is the mass of the lamina and small h is the height of that particular triangle. So this is your ixx. Similarly, if you in a similar way, if you calculate your iyy, so you will get m1 square plus 1/6 m2 b square. So in that case, you will get in terms of a and b, not in terms of h, where I have where I got here in terms of height h. So it will be the result for your yy if you calculate the iyy. And so if you write, I mean how xx, okay, now y p. Okay, so you can think it like this. So when I was calculating the ixx, in that case my formula was giving me half m1 a square, half 1 h square, so which is like this. So yeah, so which is the this base, I mean I am calculating along I-axis with a is the base and h is the height. So the first portion is giving me the base into the height square. Similarly the second portion also giving me the base, which is b times height, so bh square. Okay, I mean m2h square. Now if you consider, if you calculate I then in that case I think your height will be a1. Okay, I mean let me, so this was your part 1. So when you are calculating with this x axis, your height was h, that's why you are getting half m1 h square. Now I am just trying to give you an idea. Now if you calculate along y, so when you will calculate y, you can think the triangle like this, right? So this is your y axis and this is your x axis. Now it has been rotated. Okay, just this. So for your y axis, the height will be this part, which is a, which is a. So that's why for this case you are getting half m1 a square for the first part and similarly half m2 b square for the second part. So you can see, you can identify those m1 a square, m2 b square, why we are getting a and b here instead of h, because in this first case the height was h, but in this second case the height of the first will be a and the height will be of the second will be b, because it has been rotated. You can think of like that. Okay, so that's why you are getting m1 square and m1 a square and m2 b square. Now if you write it in terms of a total mass, then you will get, I ask you to calculate it just. So you will get 1/6 m a square minus ab plus b square. Okay, just put m1 equals to half h sigma and m2 equals to half bh sigma and then calculate it. So you will get this result. You will not find any difficulty in deriving this result. So this is the result. So for I-xx it was half 1/6 capital M h square, where h is the height and h is the height with respect to x axis, always remember that, and m is the total mass, and here Iyy is 1/6 m a square minus ab plus b square, where a and b are the base of the two portion 1 and 2. So try to visualize the image also. Okay, so this is the result. Now so we have done for a particular lamina. Now if you have given a rectangular lamina and this is the center, and you have been asked what is the moment of inertia about this line. Okay, so you can do it very easily, because it is nothing but two sum of two rectangular lamina. One is in the upper side of that line and one is in the lower side of the line. So for this first one, it will give you m1 h square if your this distance is h, let's say this distance is h, and for this part you will get m2 h square. Okay, so this is the just the application of the previous thing which we have done. Okay, so the total momentum will be, I mean let's say ABCD. So along that line I mean along the line IAC, it will be just the sum of these two, that is 1/6 capital M h square, where capital M is the M1 plus capital M1 plus capital M2, which is the mass of these two particular sections, that will give you the total mass of this rectangular lamina. So this is the moment of inertia around that line AC, okay, which is the diagonal of this particular lamina. So in the previous case we have done when the body is rotating along the center point O, but here it is rotating along the AC axis. So this is a nice application of this particular triangular lamina case. Okay, yeah, now yeah, and yes, half m h square. Okay, now let us go to uniform circular lamina. Okay. Okay, so circular lamina. So it is a circle in the xy plane, and it is z. So all your z axis are 0. Now for this you can write it rho cos phi y equal to rho sin phi, and z is z. So we are taking the cylindrical coordinate. Okay, so you know the conversion, x is equals to rho cos phi, y rho sin phi, and z equals to z, and we will calculate the zz. So zz will be coming as x square plus y square and the mass dm. So because your all the z are 0, same as the previous case, same as the previous examples. So izz x square plus y square dm, that will give you, let it is the rho. No, rho we have used once, so let us use sigma. Okay, so sigma is the density. Okay, so sigma is the density. Now elementary area, so here the elementary area will come because your dm is sigma ds. So the area for this type of system, I mean when I am using the cylindrical coordinate, it can be it can be written as rho d rho d phi. Okay, this you have already seen. Okay, so this is the thing which will come in the integration x square y square sigma rho d rho d phi. Okay, now if you do the integration, it will be rho cube d rho d phi 0 to 2 pi, and it will be 0 to r, or we have taken the radius of the circle is r. Now if you calculate, this will give you 4 by 4 times 2 pi. Okay, now the total area of this particular body is pi r square, right? Pi capital R square. And if we multiply the density per unit area with the area, that will give you the total mass of the system. So the total mass of the system is capital M is sigma pi r square. So we will write it like yes. So if you pi r square sigma, take this out, then you will be r square by 2, right? Yes, I think so. That is half m r square, where capital M is the mass of the particular laminar body, and it is your izz. So it is rotating around the perpendicular axis, I mean around that axis which is perpendicular to itself, because it is in the xy plane and z is perpendicular to the xy plane. So that this will give you izz. Now okay, now from symmetry of this system, there because this system is symmetrical, so we can write, now we will use a trick. So ixx equals to iyy. This is true for a symmetrical system, I mean this type of system which is laminar in the xy plane and it has a symmetry. So ixx plus iyy, and few example before I told you the perpendicular axis theorem, right? Ixx plus iy is equals to izz. This you can write for a laminar type body. So you have calculated the izz, and if your ixx and iyy are equal, then you can write 2ixx equals to izz, which will give you izz by 2, and it is also same as iyy. Okay, so your ixx equals to iyy is equals to 1/4 m r square. So you can see the application of the perpendicular axis theorem. Suppose you have calculated the izz, and your body is a laminar body which has symmetry, I mean a symmetrical body. Then you can apply your perpendicular axis theorem, and without doing any integration for ixx and iyy, you can very easily calculate the value of those moment of inertia along those direction. Okay, this you can also verify with by doing the whole calculation also, dm. Okay, so y square plus z square is there is no z square, rho d rho, whatever area element d rho d phi. So if you do this, you will also get the same result, 1 for m r square. So try to verify this result. Okay, so this is a good example of the perpendicular axis theorem. Now, so also you can calculate the xy, I mean ixy and xy plane yx, this you can calculate, but all the term involving z coordinate, that will be 0, because all the z are 0. So ix z zx or yz zy, those will be 0, but these two you can calculate and you can verify whether these are 0 or you are getting a non-zero value. Okay, so just do this. It will be ixy will be just xy over dm minus, that will be ixy. Okay, just try to calculate this now. Okay, now we will do same thing. Okay, now we will do for a cylinder. So all these bodies which I have talked till now, all are symmetrical body. You can see that your rod is 1D symmetrical body, but this one also a symmetrical body. But this you cannot say symmetrical, because if you consider the y-axis, that body is not symmetrical. That's why we have calculated by dividing into two parts, first and second. So that all one asymmetric body also we have done, and this is also symmetrical. So this cylinder is also we will take as a symmetric cylinder. Okay, okay, and our coordinate system is like this. This is y, this is x, and this is z. Okay, and this is r. So radius of the surface is r, and this is o. Okay, so let us calculate and say the density is rho 0, which is constant density. I will do one example of non-constant density also just after this example. So your izz will be, I mean it is revolving around the z axis, rho 0 x square plus y square, and as it is a 3D body, so I mean okay, so dm from the first principle it is now x square plus y square. Now it is not a laminar body, it is a 3D body, so it will be rho 0 dv, where rho 0 is the density of the body. Okay, and this dv you can write as, I mean x square and y square. Okay, so the same coordinate transformation we will use. This is x equals to rho cos phi, y rho sin phi, and z equals to z, because it is also we are going to a cylindrical coordinate. Then if you put all this, you will get rho square, and the dv is rho d rho d phi dz. Okay, this is d phi dz. So this our volume element in a cylindrical coordinate is rho d rho d phi dz, and the surface element is rho d rho d phi. Okay, yeah. So now if you do, so you need a height of the cylinder. Let the height is h, and that center of the system O is exactly midpoint of the cylinder. Okay, you can take a different system also where your O is suppose at this surface, and you can calculate also. There is no problem, just the limit of the integration will change. So this will be rho cube d rho 0 to r, phi is always 0 to 2 pi, and z is, so z is minus h by 2 to h by 2, because O center is the midpoint of the cylinder. So if you calculate, you will get rho 0 r to the power 4 by 4 times 2 pi, okay, times h. Now mass of this cylinder is pi, I mean volume of the cylinder, that is pi r square h times the density. So this is the mass of the system. So let us call as capital M. So if you manipulate this expression and if you want to include the mass, then you will get a result as half mr square. Okay. So this is your IZZ for a symmetrical cylinder. Okay. Now, yes. Okay. Now, it is not a laminar body, so that's why you cannot apply your perpendicular axis theorem for this particular body, which we have done in the previous example. So that's why we have to calculate Ixx and Iyy, I mean from the first principle. So remember that for the symmetry, as the body is symmetrical around the z axis, that why Ixx and Iyy are always equal, because it has a symmetry. So if you calculate Ixx, the result will be same as Iyy, and it will be same, it will be like this: y square plus z square rho 0 d rho d phi dz and 1 rho. So this rho is density and this rho is the radius vector, so don't confuse between these two. Okay. So if you do it, rho square sine square phi plus z square rho 0 rho d phi dz, and if you do the integration, I will write it from my notes. 2 pi, just check, and if there is any mistake, just let me know. Dz, this is the first term, plus rho d rho minus h by 2 j square dz, this is the second term. So if you calculate and properly, then you will get this result. Just do this, so that will give you a square by 12 plus r square by 4. Okay, so this is also same as Iyy. So you can see that your Ixx is much more complex than the Izz for this particular cylindrical system. Okay. And it is very easy to do it, but always remember, here you cannot apply the perpendicular axis theorem, as it is not a laminar body. Okay. So and you can calculate the Ixy and I mean all the cross product also, and you can see whether those are 0 or not. So just remember, for a symmetrical body, if xy are symmetry, xy have any symmetry, then you will get a 0 result, but I will ask you to check whether you are getting it 0 or not. Okay. So for this case, for the symmetry, you will get 0. For the xy coordinate, it is coming from the symmetry, and Izx and Iyz, these are 0. These are coming because these are coming also for symmetry, because it is not a laminar body, and no z equals to 0, that we cannot write in this case, because all the z's are non-zero. So you will calculate Ixy, Ixz and Iyz, and all will, so and you can see that all the values are 0 for the symmetry. Now for very short, we will do the same example but with the non-constant density. So suppose say our density now is a function of z, that is rho 0 minus 1 by 2 z by L, this type of, where L is the length of the cylinder. Okay. I mean, instead of h we have used L, because it was given L in the problem from where I have taken it, so I have not changed that. Now what will be your Izz? So from the first principle, it will be same, rho dash z dv. but here you cannot take your rho out of the integration, it will be inside the integration, right? And it is rho 0 1 minus half z by L dv rho 0 d phi dz. This rho 0 you can take out because this rho 0 is constant. Okay. So rho 0, this x square plus y square with the proper transformation, that is x equal to rho cos phi, y equals to rho sin phi, will give you rho square. Okay, and 1 minus half z by L is there. Then there is another row, that is rho cube. I have used this row also, and there is d phi dz. Let me check. Yes, so if you do it, rho 0 rho cube d rho d phi 1 minus half z by L dz. Okay, yes, so rho is 0 to r, 0 to 2 pi, and yes, just a second. Yes, okay, and here you can you can use your coordinate system at the center, as I have shown in the previous case, but in this problem let us consider that we are measuring our z from the bottom of the cylinder. Okay, so our coordinate system, center of the coordinate O, is at the bottom of the center. Suppose we consider like that, then it will be 0 to L. If you consider from the midpoint, then it will be minus L by 2 to L by 2. Okay, so actually it has been taken from bottom to the up, so that is 0 to L. Now if you calculate, so we have modified two things. One, we have changed our coordinate system from center to the bottom point, and instead of a constant density, we are using a density which is a function of the vertical distance. So that will be, if you do it, 1 by 2L L square by 2, which will give you 38 pi r to the power. I am writing it from my notes, that's why I am writing it so quickly, so you can verify it. I just want to tell you the result, what is the physical significance of the result. So it is your izz when your rho is not a function of rho is a function of z. Now mass of this cylinder, for this cylinder you cannot write your mass is pi r square, pi r square into length into rho. You cannot write it like this because your rho is not constant anymore. So for mass you have to calculate also, which will be d rho d phi dz. This is your mass, which is the volume integration over the volume integration over the whole volume with the given density. So if you calculate it, then you will get rho d rho d phi 1 minus 1 by 2 z by L dz 0 to L 0 to 2 pi 0 to r, and 1 rho 0 is there. So if you calculate this, I am not doing it, you will get a result like 3 by 4 pi r square rho 0 L. Okay, so now okay, one step I should write, you verify it. It will come like this, L minus, oh just a second, it was L, L minus, as I am not doing this, that's why there may be mistake. So this will give you 3 by 4 pi r square rho 0 L. So now we will put this into this result, which will give you half m r square. Okay, so you are getting izz equals to half m r square, where m is the mass of the cylindrical body, r is the r is the radius of the flat surfaces, this one, top and bottom flat surface, and m is the mass, as I told. But here remember, this result we have got from a non-zero non-uniform density. So the main point is this. So where we have not considered rho equals to rho 0 anymore, but we have given a dependence of the distance, vertical distance. So from here we have calculated. Okay, so this was the result for the cylinder. Now in the next class we will do some problems, I mean some physical problems using this moment of inertia tensor, like a cylinder is I mean it is put on a plane which is making some angle with the horizontal, and it is coming down from the top of the plane. So this type of problem, with the help of this moment of inertia, we will do it, and we will do some more problems of the moment of calculation of moment of inertia, like a cone, I mean more difficult problem which are for a cone and for a hollow cylinder and for a hollow sphere, for a solid sphere, and we will try to see some application of this moment of inertia in these problems, physical problems. Okay, so today I will end the session here, and thank you.